Okay, so good morning. Before we start, let me discuss to you um, what are the basic, okay, serological reactions. So for the basic serological reactions, we have precipitation, and then we have agglutination, then we have complement fixation, then we have um, the labeled immunoassays. So for today, we'll try to touch precipitation and agglutination. And also, I will give you an example of the complement fixation test. Okay. So let's talk about So for the summary, uh, we will be having the following: antigen-antibody binding, precipitation curve, light scattering technique, passive immunodiffusion techniques, electrophoretic techniques, agglutination reaction, instrumentation, and some of the principles involving the quality control and quality assurance. Okay, so let's define first the term affinity. Okay, so let's define first what do we mean by affinity. So when we say affinity, we are referring to the initial attraction. Okay, so when you say initial attraction, it is the first time that antigen and the antibody meet. Okay, so that's the initial attraction. Okay, it's the first instances that they have actually met. So there is an initial attraction force, okay, between FAB site, an antibody molecule, and epitope or determinant site of an antigen. So if this is for example is an antigen, and this would be the epitope. So the first time that they meet, okay, is actually called affinity. Now, the thing with affinity is that affinity is something that is reversible. Okay, so when you say reversible, it means that they can still be dissociated. They can still be dissociated. Okay, so but anyway, the first time that they meet, we call it affinity. So the strength of attraction depends on the specificity of the antibody for a particular antigen. So if the antibody would be very specific to the epitope of a certain antigen, for example, then the affinity would be much stronger. Also, the more cross-reacting antigen resembles the original antigen, the stronger the bands will be between the antigen and the binding site. Okay, so let's define first what do you mean by cross-reacting antigen and what is the original antigen. So when you say original antigen, it is the first antigen that causes antibody attraction. Okay? So siya talaga the one that initiates antibody attraction. So that's what you call the original antigen. However, when we say cross-reacting antigen has some similarities. They have some similarities with the original antigen. They only have similarities with the original antigen. And since they have similarities with the original antigen, they tend to mimic the original antigen. And since they mimic the original antigen, there's a possibility of cross reactions. Okay? So, what is the implication of having cross reactions? Well, that is not somehow good on the context of serological tests because cross reactions can somehow result to false positive reaction. And of course, if the reaction is false positive, then it is not anymore accurate. So it is not anymore accurate kasi nga it is false positive. Okay. So the thing that I'm trying to emphasize here is that if the cross-reacting antigen resembles the original antigen, the more resemblance that they have. So if there are more resemblance, then the stronger the band will be between the antigen and the binding site. So more resemblance means more possibility, more possibilities of false positive reactions. Okay, so that's what we meant by more resemblance because of the similarity. Now take a look at the illustration that we have here. So here you have higher affinity, okay, as compared to the lower affinity because higher affinity means that um, the epitope is highly specific. So let's say the triangle here represents the epitope. The epitope here is highly specific, highly specific for highly specific for the antibody, the FAB portion of the antibody. Take note also that positive forces will attract negative forces. So if the epitope here is positively charged, then it will bind to the negatively charged FAB portion. So in this case, the epitope here is negatively charged, then it will bind with the positively charged portion of the FAB. But in this particular illustration, you have an epitope that is both negatively charged, then it will only bind to a certain part of the FAB, not on the entire part. So this results therefore to lower affinity. Okay, so positive forces attract negative forces. So that's the principle in affinity. Okay, so we have already defined affinity. Let us now define what do we mean by avidity. Okay, so avidity is the sum of attractive forces between an antigen and an antibody that keeps the molecules together. So just to give you a scenario, if this antibody binds with the antigen, the individual antibody that binds here, that only refers to affinity. However, some of the antibodies are multivalent, such as IgM. If you remember IgM is multivalent. All antibodies are multivalent, but IgM is the most multivalent of them because of because of it is considered to be as a pentamer. So if the one antibody binds here, and some antibody binds here, okay? So there are multiple binding sites, okay? So there are, in this particular illustration, there are multiple binding sites, okay? And since there are multiple binding sites, It will keep the molecule together. Therefore, avidity doesn't only refer to the individual binding of the antibody and antigen, but it refers to the overall strength. Okay, the overall. Okay, because it involves the strength in which multivalent antibody binds with multivalent antigen. So for example, you have here an antigen. An antigen would have several epitopes. Okay, so there would be several antibodies that can bind with an antigen. Or there's even a possibility that one FAP will bind to this antigen and another FAP will bind to this particular antigen. Do you get my point? So that's what you call avidity. Okay? And that particular ability is the measure of the overall stability of an antigen antibody complex. Okay? So that's why they say IgM would be more efficient in agglutination, for example, because it is a pentamer and has several multiple binding sites. Okay, so that's what we meant by avidity. Okay, so the antigen antibinding complex follows the law of mass actions. Okay, so free reactants are in equilibrium. I'm sorry. Free reactants are in equilibrium with bound reactants. Okay. So what do you mean by how do you know if it's a free reactants and bound reactants? So when you say free reactants means that either the antigen or antibody are or is unbound, meaning to say they haven't found any affinity yet. So the value of this particular K or equilibrium constant depends on the strength between the antibody and the antigen. Okay? So the larger the amount of antigen complex, the more visible or easily detectable the reaction. So meaning to say, you'll be able to see visually through your naked eyes agglutination or precipitation reaction if there are more antigen and antibody that will bind together. If only few of them will bind, then you'll not be able to see any reaction at all. So that's what we meant by the law of mass actions. So the larger the amount of antigen and antibody complex, the more visible or easily detectable the reaction would be. Okay. So let's discuss first precipitation reaction. Okay. So precipitation reaction involves combining a soluble antigen. So we will now be combining a soluble antigen with a soluble antibody to produce an insoluble complex that are visible. Okay, so that's what we meant, ha? So take note of the term soluble. So the soluble antigen is defined as precipitinogen, while the soluble antibody is known as the precipitin, and the visible reaction is called the precipitin line. Okay, so in precipitation reaction, therefore, you'll be able to see a precipitin line. So a precipitin line is a positive reaction and it indicates the binding between a soluble antigen and a soluble antibody. Okay, so that's the positive reaction in precipitation reaction. So, what are the requirements? So, aside from the fact that in precipitation reaction requires the antigen and antibody to be soluble, so requirement is that there should be a multiple binding sites for one another. So, say multiple binding site, okay, uh, multivalent, should be multivalent. And another requirement is that there should be an equal relative concentration of each. So when you say equal relative concentration of each, it means that both the antigen and antibody should achieve the so-called zone of equivalence. Okay, so both the antigen and antibody should be able to achieve the so-called zone of equivalence. Okay, so without the zone of equivalence, will not be able to achieve, okay, precipitation reaction. Okay, so what do we mean by the zone of equivalence? Okay, so this is now the zone of equivalence. Okay, so when you say the zone of equivalence, the number of multivalent sites of antigen and antibodies are approximately equal. Okay, so when you say approximately equal, so there is what? An optimum concentration of antigen and antibody. So if there is an optimum concentration of antigen and antibody, you have already achieved the zone of equivalence. Okay. So, however, there is what you call prozone. Okay. So, prozone is the zone of antibody excess. That's prozone. And then we also have the post-zone. Okay, so post-zone is the zone of antigen excess. We do not want to have prozone and post-zone because both prozone and post-zone will result to false negative reaction. If kanina, cross-reacting antigen results to false positive reaction, prozone and post-zone will result to false negative reaction. So, excuse me, if there is a false negative reaction, it means that there is no visible reaction because of too much antibody or too much antigen. Because in order to be detectable, precipitation reactions must run in the zone of equivalence. So if you have too much antibody or too much antigen, then it will not result to zone of equivalence. Okay, so let's talk about first the prozone. So prozone phenomenon is the zone of antibody excess. So antigen combines with only one or two antibody molecules. So meaning to say there is too much antibody. There's too much antibody, no cross linkages are formed. Okay? And false negative reaction may occur as a result of high antibody concentration. Okay, high antibody concentration, or meaning to say, antibody titer is high. So if the antibody titer is high, or if you are if you are suspecting that the the serum that you are doing or that you're assaying is has a very high concentration of antibody, therefore dilution would be very important. Okay, so to resolve false negative reaction, diluting out the antibody and performing the test again may produce a positive result. So serum dilution or specimen dilution, not necessarily serum, would be the solution to prevent prozone phenomenon. Okay, what do I mean for this one? No? So, for example, 1:1 dilution, you have 1:2, you have 1:4, and you have 1:8, you have 1:16. So when you are doing the 1:1, it's negative. And then when you start diluting, when you say 1:1, 1:1 is the undiluted. But when you started, and then even 1:2, it's still negative. But when you start diluting it, becomes positive until such time that 1:30 is negative. Meaning to say, the first two dilutions, it is a zone of too much antibody. That's why it's negative. So by performing serum dilution or specimen dilution, in this case, we call it serial dilution. By the way, serial dilution is the lesson that we had in chapter 9. So hope you can recall our lesson there in chapter 9. So by doing serial dilution, then we can actually resolve the prozone phenomenon. Okay, now let's talk about the Bozone phenomenon. So when we say Bozone phenomenon, this time we are talking about the zone of antigen excess. So small aggregates are surrounded by excess antigen. So there is no lattice formation. By the way, what is a lattice formation? So when you say lattice formation, we are referring to the cross linkages between the antigen and antibody. And lattice formation can only be achieved if there is a zone of equivalence. So lattice formation can only be achieved if there's a zone of equivalence. Okay? So remember, in both prozone and pozone phenomenon, you will not be able to achieve lattice formation. So the presence of a small amount of antibody may be obscured. Kasi you have too much antigen. Okay, so you have too much antigen. So it will be obscured, causing false negative results. So what should be the resolution? First, you can repeat the test. About a week later, why do you think the test is repeated? Because there's a possibility that you perform serological tests too early. If you perform serological tests too early, your body has not produced antibodies yet. So when you test it, it is negative. So that could be a Bozone phenomenon. So you postpone, you perform a week later, and if the test is negative again, it is unlikely that the patient has the antibody. Or this would be the first resolution. The second resolution, you can do cell washing. You can do cell washing, meaning to say you wash RBC with saline solution or the normal saline solution 3 times. So that's actually one of the activities in serology and in blood banking. So there should be cell washing so that we try to remove excess antigen. Okay, so cell washing is actually most likely the one that we're using usually in blood banking, or for example in blood typing, we're doing the cell washing. But if you perform serological test too early, means that your patient hasn't developed antibodies yet, most likely it will result to false negative result. Okay, so these are the different types of precipitation reactions. So we have the nephelometry. It can be applied for the assays of immunoglobulin, complement C-reactive protein, and other serum proteins. So in nephelometry, the light that is scattered at an angle is measured, indicating the amount of the antigen or antibody present. So for example, um, this is the solution. Okay. And here's the light. Okay, so if you apply light here towards the solution, okay, and then there are precipitation reaction here, some of the light will pass through. Okay, this is the scattered light. Scattered light means that this light was able to pass through the solution. Then some of the light will be blocked. So we have also the black light. So when you say black light was not able to pass through the solution. Why they are black? Due to precipitation. They were black due to precipitation. So light that was able to pass through, when we are measuring it, we call it nephelometry. We are measuring the scattered light. But if we are measuring the black light, the technique is called turbidimetry. Okay, I hope that's clear. If we're measuring the scattered light, we call it, this is a light, okay? This is a light, okay? So if we're measuring the scattered light, you call that nephelometry. If you're measuring the black light, meaning to say light that was not able to pass through the solution due to the precipitation reaction, then that is what you call turbidimetry. Okay. So it says here in turbidimetry, light that is scattered at an angle is measured, indicating the amount of antigen or antibody present. Meaning to say, the more scattered light is present, then the more amount of antigen or antibody is present. Okay. So let's talk about radial immunodiffusion. Radial immunodiffusion is used for measuring immunoglobulins and complement. It is also, the sensitivity is between 10 to 50 microgram antibody per ml. So the principle is that antigen diffuses out into a gel that is infused with antibody. Okay, so it is infused with antibody, and since it is infused with antibody, um, it is diffused. It is infused with antibody. There would be a precipitin line. So what we're doing here is that we will be measuring the radius, which indicates the concentration of antigen. So here's an example of radial immune diffusion. Okay, so let me explain that to you in detail. So radial immune diffusion is a single diffusion technique. Okay, um, antibody is in the support gel and the antigen is applied in a well cut in the gel. Okay, so this is the gel. So the antibody is present in the gel and the antigen is applied in the gel. Do you get my point? So this is the gel and the gel contains antibody and the antigen is applied in the cup. There would be a hole. Okay, so if we're going to look at the side view, so there's a hole. Gato na lang. So this is where you apply the antigen. And this is the gel, and the gel contains the antibody. Okay. Antigen will diffuse out until the end point of the equivalence is reached. So we will be measuring the square of the diameter, which is proportional to the antigen concentration. Meaning to say, the wider the diameter, then the more concentrated, the antigen is. Okay, so that is the principle in radial immunodiffusion. So, for example, in order to measure it, in order to measure the concentration of the reactant, we compare it to a set of standards. Okay. So when you say standard, a standard is a substance of known concentrations. Let's say, for example, standard number 1 has a concentration of 6 milligrams per DL. Standard number 2 has a concentration of 15 milligrams per DL. And standard number 3 has a concentration of 25 milligrams per DL. So we measure the diameter. Of the three standards. Say, for example, standard number 1 has around 10, or let's say it's 8. So 8. Standard number 2 is 15. Standard number 3 is 18. So if the standard number 1 has 8 millimeter, so we place it here. Kasi this is the 8 millimeter, no? So standard number 2 has 15 millimeter. So we place it here, 15. Kasi nga, tapos 15 din yung milligrams per DL niya. Standard number 3 is 25 and it measures 18. Nandito yung 18, kaya we place it here. And then, this is now your patient. Unknown is the patient sample. So, let's say the patient sample, the diameter of the patient sample is, let's say, 12 millimeter. So, nandito yung 12 millimeter, tapos dito pumatak. So, most likely, the concentration of the patient is 11 milligrams per DL. Okay? So this particular graph is what you call the standard calibration curve. Okay, which you can actually do standard calibration curve. Okay? So for your activity later on, you will be doing a standard calibration curve using a graphing paper. So I will give you the concentration of the standard, and I will give you the diameter of the unknown, so that you'll be able to measure the concentration of the unknown. Okay, so that is the radial immunodiffusion. Okay, so again, radial immunodiffusion is also known as the single immunodiffusion. Okay, so let's talk about the Australoni. So Australoni is also known as the double diffusion. Okay, so the Australoni is also known as the double diffusion. So it is applicable for complex antigens such as fungal antigens, and its sensitivity is between 200 to 220 to 200 microgram of antibody per ml. Excuse me. So both both antigen and antibodies diffuse out from well in a gel. So the line of precipitate form indicate the relationship of antigens. Okay? So saglit lang guys. So this is an example of the Australoni, also known as the double diffusion. So it is the double diffusion technique. So what will happen here is that wells are cut in a gel, and both antigen and antibody diffuse out radially. So you have here a gel, and you have three wells, or you have three holes. Okay, and a line of precipitate forms where antigen and antibody meet. So if the antigen and antibody meet, okay, so there would be now a precipitin line. So if antigen and antibody meet, there would be a precipitin line, and you'll be able to identify three possible patterns. So the three possible patterns are identity, partial identity, and non-identity. So this is what you call serological identity. Okay? So in serological identity, there is what you call a arc. So there's an arc. Okay, so if there's an arc, meaning to say, um, meaning to say, there is serological identity. Meaning, this antigen is identical with this antibody. This antigen is identical with this antibody. Okay, so the arc is actually a precipitin line. This is where antigen and antibody meet. Okay, non-identity would appear like this. So this is described to be as the cross line, meaning to say the antigen present in well 1 and the antigen present in well 2 is not identical with this particular antibody. So that's why it's called cross line. So it means that they are not really they are not really related with the antibody that is present here. Okay. Letter C is called partial identity. So this particular formation, yung ito, this is what you call the spore formation. Spore formation means that only one of the antigen, only one of the antigen is identical, okay, with the antibody. So that's why it's called partial identity. Okay, so in this particular example, only antigen 1 is identical with the antibody, and the other one is not identical. Hence, there is a spur formation. Okay, so that is the Australoni patterns. So the Australoni patterns, okay, is applicable for complex antigens such as fungal antigens. Okay, so we also have immunoelectrophoresis. Do you know that electrophoretic method, okay, is the most accurate method of precipitation reaction? So anything that involves electrophoresis is considered to be as the most accurate. So here, the application of immunoelectrophoresis and immunofixation phoresis. So immunoelectrophoresis is used for the differentiation of serum proteins. Immunofixation electrophoresis is used for over or under production of antibody. So the sensitivity range of immunoelectrophoresis is between 20 to 200 microgram antibody per ml. And the principle of immunoelectrophoresis is you allow electrophoresis of serum, and then it is followed by diffusion of antibodies from the wells. So antibodies will diffuse out of the well. Okay. Whereas in immunofixation phoresis, electrophoresis of serum is followed by direct application of antibody to the gel. Meaning to say, antibody will not anymore diffuse out from the well. Okay, so I hope you get the difference between immunofixation. This one would be coming from the well, and then here in immunofixation electrophoresis, there is direct application of antibody to the gel. So let's discuss them in detail. Okay, so immunofixation electrophoresis is a double diffusion technique. However, in 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 radial immunodiffusion and double immunodiffusion, we do not apply electrical charges. But here, we apply electric charge. Why do we need to apply electric charge? Electric charge will facilitate or will speed up the meeting of antigen and antibody. There is a technique in radial immunodiffusion that you have to wait for 3 days before you can see a visible reaction. Imagine, no, you have to wait for 3 days. But kasi radial immunodiffusion is either the Mansinai or the Fahey method or the endpoint or the kinetic method na kailangan you have to wait for 3 days. You have to wait for 24 hours. But here, in immunofixation electrophoresis, just need to wait for several hours, not for a day, not for 3 days. So the principle is that a known antigen is allowed to electrophorese, and then the antibody is applied directly to the gel. Okay? So that is immunofixation electrophoresis. Immunoelectrophoresis, the antibody will diffuse out from the well. But here, we're talking about immunofixation electrophoresis. So precipitate is formed where the antigen and antibody combined has taken place in the gel. So this technique is used with serum. So serum, therefore, will be the source, will be treated like an antigen to determine over or under production of antibody types. So meaning to say, in immunofixation electrophoresis, patient serum is electrophoresed in the gel. So patient serum is electrophoresed in the gel. Okay, here in immunofixation electrophoresis. And by the way, the principle of electrophoresis is that it is the migration of protein in an electrically charged field. Okay, it is the migration of protein in an electrically charged field. So that's the principle of electrophoresis, meaning to say, the bigger the molecular weight, the larger the molecular weight, then the smaller, the slower the migration would be. So in this case, this is an example of immunofixation electrophoresis. Okay, so this is the standard. Okay, so this is the standard. So the standard will allow us to determine. The standard contains all the bands. These are the bands, no? So, for example, in this particular patient, in this particular patient, you would see that um, the gamma band is present. So, ibig sabihin, there is an overproduction of IgG. Kasi makita nyo rito. Ito naman, um, yung letter A, alpha, uh, and letter M, itong dalawang to, merong underproduction of antibodies. Kasi wala kayong makitang bands. And then this is where the kappa band should be. And this is where the lambda band should be. Ito naman, made up the light chains of antibodies. So dapat, kung normal patient ka, ganito dapat yung itsura ng electrophoresis mo. Ibig sabihin, lahat ng antibodies meron ka, and then lahat ng meron ka rin ng kappa and lambda. So ibig sabihin, kompleto ka ng antibodies. So immunofixation electrophoresis, therefore, will allow us to assess over or underproduction of antibodies. Okay, so that is for precipitation. Okay, so later on I will let's now discuss agglutination reaction. Okay, so let's differentiate agglutination from precipitation reaction. Okay, so the antigen here is called agglutinogen, and the antibody here, the antigen here is called precipitinogen. And precipitinogen is said to be soluble, and agglutinogen is said to be particulate. So the antibody here is called agglutinin, and here in precipitation reaction, it is known as precipitin. Okay, so if you notice, no, in antigen, it involves particulate antigen and antibody reaction. In precipitation, it indicates or it involves soluble antigen and antibody reaction. Therefore, the result here would be what? Agglutination or clumping. You'll be able to see visible agglutination or clumping. But in precipitation reaction, you'll be able to see precipitin line. Okay, so that's the basic difference between agglutination and precipitation reaction. Okay, so therefore, if you'll be defining agglutination reaction, is the visible aggregation of particles by resulting from combination with specific antibody. So just like your precipitation reaction, agglutination reaction is a two-step process because this one involves sensitization or the initial binding. Okay, so here, like what I've told you, antigen and antibody unite for the first time through antigenic determinant sites, or this is what you call epitope. Sensitization is still reversible. And then, second step is the lattice formation. Here, you would notice that there is now already a formation of large aggregates, meaning to say, rearrangement of antigen and antibody bonds to form a stable lattice. Again, let me reiterate to you that in order to achieve lattice formation, you should be able to observe the so-called zone of equivalence. So I think I've already told you the agglutination reaction is produced by antibodies called agglutinins. So we call them agglutinins. Okay, so the antibodies that are involved in agglutination reaction, we call it agglutinins. So here's an example of a very simple agglutination reaction. So if this is your antibody, and then this is your antigen with multiple determinants. So you have a determinant here, 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 and here. So there is the first step is called sensitization, meaning to say there is no visible reaction yet. And then the second step, there is now a lattice formation. So in lattice formation, you'll be able to see visible agglutination or visible clumping. So you'd be able to see visible clumping of the antigen. Okay, so that is agglutination reaction. There are several types of agglutination reaction. There are several types of agglutination reaction. Wala tuloy. Okay. One example is called direct agglutination. So direct agglutination would be of two types. It could be the direct bacterial agglutination, and the other one is the hemagglutination. So obviously, the antigen here would be bacteria, and the antigen in hemagglutination would be red blood cells, the RBCs. Okay, so let's talk about first the direct bacterial agglutination. So it uses known bacterial antigen to test for the presence of unknown antibodies in the patient. So perhaps one of the most common example is without test, though without test is already passé, but it is actually being done, excuse me, as a rapid screening test used to determine the possibility of having typhoid fever. Okay, so the without test uses Salmonella O. So the O antigen is the somatic antigen. If you can recall our bacteriology, somatic antigen actually came from the cell wall. And there's another one, the H antigen or the flagellar antigen. So obviously it came from the flagella of the bacteria. Okay, so aside from without test, Will Felix test. Okay, so it is for rickettsia. And this time it uses Proteus antigen. There is also an agglutination test for Leptospira antigen. So practically, any bacteria can be utilized as a source of antigen for direct bacterial agglutination. So here is an example of the without test. So in the without test, you can either do it using the tube method. So this is the tube method. And then this is the slide method. So you'll be able to see. So let's say, for example, this is the agglutination with the O antigen. And then you'll be able to see agglutination with the H antigen. Here, you'll be able to see clumping. You'll be able to see clumping. Okay? So that is an example of direct bacterial agglutination test. Okay, so that's the without test. So another example of direct agglutination test is the hemagglutination. So this time, it involves RBC as the antigen itself. So the most common example of hemagglutination is when you perform blood typing. Okay? So why? Because the surface of RBC is the source of antigen, while the anti-sera, so you can either use anti-A or anti-B or anti-D for RH typing. Okay, the anti-sera would be the source of antibody. Okay, so that is the direct agglutination reaction. Okay, so you can actually do hemagglutination either using the tube method or the slide method. But do you know that the tube method is actually more accurate? Though the advantage of the slide method is that you can actually check the agglutination under the microscope. So the advantage naman of the tube method is that you can centrifuge the tube. Okay, after you have centrifuged the tube, you'd be able to see cell button. Okay, the button of cells. And then you can shake the tube. And if there's one solid clump, okay, that would be graded as +4. If there are several large clumps, that would be graded as +3. If there are numerous smaller clumps, that would be graded as 2 plus. Barely discernible clumps, that would be graded as +1. Negative means there's a smooth suspension. So you can actually shake the tube and then interpret the clumping. Okay? Or if you're using the slide method, you can actually see also without using the microscope the agglutination. However, if you are doubtful if agglutination is present or not, then you can always look, okay, under the microscope. Okay, so under the microscope, if RBC do not overlap, that is considered to be as a negative reaction. Okay. So also, you'll be able to differentiate agglutination from the rouleau formation. If you look under the microscope, okay, this is this is the spelling of the rouleau formation. Rouleau formation means that the RBC appears like a stack of coins. This is usually seen. This is usually seen if you are using cord blood because that is from the neonate, because that is very viscous and high in protein, and because of the presence of Wharton's jelly. So during agglutination reaction, if you are able to see rouleau formation, so the best thing to do is cell washing. Meaning to say you wash RBC 3 times with NSS or the normal saline solution. So that's the solution that we are doing for the rouleau formation. Okay. Now let's talk about passive agglutination. So this is now the second type of agglutination because the direct bacterial and hemagglutination is just a subtype under the direct agglutination. So here, in passive agglutination, we employ particles that are coated with antigens not normally found on their surface. So RBC and bacteria, okay, have antigen on their surfaces, have a natural, antigen on their surfaces. Therefore, we can say we can do the direct agglutination. But there are some antigen, okay, there are some particles that do not have antigen, not normally found in their surfaces. And we cannot see visible reaction without using these particular particles. And the possible particles that we will be using are the erythrocytes, the latex, gelatin, and silicates. So for those of you who will be doing limited face-to-face, majority of the agglutination reaction that you will be doing in the laboratory is the latex agglutination. So you would notice that it is a latex because you'll be able to see a creamy white fluid. So you will be doing a passive agglutination. So erythrocytes, latex, gelatin, silicates, okay, this serves as the indicator so that you'll be able to see visible reaction with your naked eye. You don't have to use a microscope to see a visible reaction. So the common denominator of erythrocytes, latex, gelatin, and silicates that they are actually synthetic beads or particles, and they provide consistency, uniformity, and stability. Okay? So that is passive agglutination. So passive agglutination can actually detect rheumatoid factor, antibodies to group A streptococcus antigen, okay? Antibodies to viruses such as rotavirus, cytomegalovirus, rubella, and varicella zoster, and antibodies to hepatitis viruses and HIV. So the process, the antigen is attached to the carrier particle and agglutination occurs if the patient antibody is present. So this, okay, so the antigen is attached to the particle. So the sensitized particle could be a latex particle. If the patient's antibody is present, then there would be a lattice formation. And if there's a lattice formation, then you'll be able to see visible clumping or visible aggregate. So this is passive agglutination. Okay. So there are actually another variation of passive agglutination. This time, it is called now reverse passive agglutination. So do not get confused. So let me go back to the passive first. In passive, antigen is attached to the carrier particle. Okay? That is for the passive agglutination. For the reverse passive agglutination, antibody is attached to the carrier particle. Okay, so it is used to detect microbial antibodies, and common applications would be rapid identification of antigen from infectious agents such as group B Streptococcus, Staphylococcus aureus, streptococcal groups A and B, rotavirus, Cryptococcus neoformans. So here we can detect soluble antigens in urine, spinal fluid, and serum. Agglutination occurs if the antigen is present in patient sample. Okay, so again, in passive agglutination, the most common specimen is patient serum, because patient serum is the source of antibodies. In agglutination reaction, okay, specimen are urine, spinal fluid, and serum. And this particular specimen are the sources of antigens. Okay, so that is the reverse passive agglutination. So if we will be comparing passive and reverse passive agglutination, you would notice that in passive in passive agglutination, the carrier particles such as the latex particle is mixed with soluble antigen. And if they are mixed with soluble antigen, you now have the coated particles. Okay. Then you add the patient sample that contains serum. If the patient is positive with antibody, there would be agglutination. However, in reverse passive agglutination, this time the particles, such as the latex particles, are coated with antibodies. And then we get patient sample, such as urine, CSF, or even patient serum that could possibly contain patient's antigen. And if the patient has the antigen, there would be lattice formation and agglutination reaction will occur. Okay, so that is the difference between the passive and reverse passive agglutination. Okay, so let's talk about agglutination inhibition. Okay, so this is what you have to remember about agglutination inhibition. In agglutination inhibition, so the keyword here is inhibition, means that no agglutination or lack of agglutination is considered to be as a positive reaction. How does it happen? Because of the competition between particulate and soluble antigen for limited antibody combining site. And it is useful for the detection of antibodies against certain viruses, such as rubella, mumps, measles, influenza, parainfluenza, hepatitis B virus, herpes virus, respiratory syncytial virus, and even adenoviruses. Okay, so that is agglutination inhibition. So what do I mean when I say competition for a limited binding site? Okay, let me present to you two scenarios. the first scenario is an example of a positive reaction. Here, the patient sample contains antigen. Okay, let's say the antigen that we have here is HCG. It is a human chorionic gonadotropin. It is a hormone found during pregnancy. So, in serological reaction, even if you are detecting hormones, you can also treat that hormones as an antigen in the context of serological reaction. Okay. So, let's say the patient is pregnant. So this is a urine sample. And the patient has antigen, sorry, which is the human chorionic gonadotropin. And then you add anti-HCG. What is the source of anti-HCG? Anti-HCG is reagent 1. So what will happen is that the HCG of the patient binds already with anti-HCG. Okay, so HCG is already combined with anti-HCG. Is there an agglutination? Yes. Okay, so there's an agglutination. This agglutination is called immune complex. The question is, we cannot see immune complex through our naked eye. You cannot see HCG in the urine. It's a hormone. You cannot see the anti-HCG in the urine. So yes, there is an immune complex, but you cannot see the reaction. That is the reason why we have now to add an antigen coated with particles. So this is now, let's say for example, a latex particles. These are latex particles coated with HCG. However, they will not actually clump because all of the antibodies are already busy with the HCG coming from the patient. So there is no agglutination. No agglutination is a positive test because HCG is present. Ibig sabihin, the patient is pregnant. Let's take a look at a negative sample. Here's how a negative sample will look like. So this is the patient urine. And since the patient is not pregnant, then the HCG is not present in the urine. So even if you add a reagent antibody, it will remain unbound. So unbound, meaning to say, there is no immune complex. And then, you will now be adding latex particle coated with HCG. So this particular latex particle will now form cross-link or lattice formation with the reagent antibody, and there is an agglutination reaction. So here, you'll be able to see visible agglutination. However, the visible agglutination that you are seeing here is an indicator of a negative reaction because in the first place, this patient doesn't have any HCG in the urine. Okay, I hope that's clear, huh? This is an example of agglutination inhibition. Okay. So you can also use agglutination inhibition for viral antigen, for viruses, okay? So what is the agglutination inhibition for viruses? We call it viral hemagglutination inhibition. Okay? And the viral hemagglutination inhibition is actually helpful for the detection of viruses with viruses with hemagglutinins, meaning to say they can agglutinate RBC. An example of viruses with hemagglutinin, an example of these viruses are orthomyxovirus. So orthomyxovirus is an example of virus with hemagglutinin that can agglutinate RBC. And or orthomyxovirus is katulad ng H1N1 or yung tinatawag natin na influenza virus. So this particular viral hemagglutination inhibition can detect antibodies from the patient. So we can detect if the patient has antibodies. So let's say, for example, this is a serum, and this patient is positive with viral antibodies. So you notice that this patient has antibodies, and then you add viral antigen. So this is now your reagent 1, and this is your reagent 2. Okay. So viral antigen, okay, viral antigen contains hemagglutinin. Viral antigen, is the viral particles. And the source of, and viral particles serve as the source of antigen. Kaya nga siya tinawag na viral antigen. So if this particular viral antigen is specific with the antibodies coming from the patient, you will see that there would be immune complex. So immune complex form. However, the reaction is not visible because you'll not be able to see viruses under the microscope. So that's invisible reaction. So that's the reason why we add RBC. However, since the antibodies are used up already, RBC will remain unbound. So this is therefore an example of a negative, this therefore is an example of a positive reaction. So no RBC agglutination is an example of a positive reaction. Now, take a look at result B. Result B, the serum here has no antibodies. So even if you add viral antigen, your reagent 1, you will not be able to form an immune complex. Therefore, if you will be adding RBC, the RBC will be agglutinated by the virus because the virus contains hemagglutinins, and hemagglutinins can agglutinate RBC. Agglutination of RBC, however, is a negative reaction because it can only happen if the serum doesn't have any antibodies at all. Okay, so this is an example of viral hemagglutination inhibition. Okay, so therefore, to summarize what we had just discussed, direct agglutination involves antigen that is naturally found on a particle, such as bacteria and RBC. Agglutination indicates the presence of a patient's antibody. Indirect agglutination is also known as passive agglutination. Okay, particles are coated with antigens not normally found on their surfaces. So the most common example of particles are latex particles, though we can use gel, silica, and RBC as well. So agglutination indicates the presence of patient's antibody. Reverse passive would also utilize particles. However, the particles here are coated with reagent antibody, unlike in indirect agglutination, which is coated with antigen. So, agglutination here indicates the presence of patient's antigen. Okay, agglutination inhibition. So, haptens are attached to occurrer particles, and particles compete with patient's antigen for a limited number of antibody sites. So, the lack of agglutination or no agglutination indicates a positive reaction, which means that the presence of patient antigen is positive. So, hemagglutination inhibition is more appropriately termed as the viral hemagglutination inhibition, wherein RBC spontaneously agglutinate if viral particles are present. So, lack of RBC agglutination indicates the presence of patient's antibody. So, I hope that it is clear. The types of agglutination reactions are clear. But do you know that majority of these agglutination reactions are being utilized, are actually being observed using our naked eye? However, there is an instrumentation available for agglutination reaction, and this is the PASIA, the particle counting immunoassay, which utilizes the principle of nephelometry. So remember, the principle of nephelometry, it is the measurement of a scattered light. Okay, so there's a light because it involves a laser in an optical particle counter to measure the number of residual non-agglutinating particles in specimen. So PASIA is very useful for the measurement of serum protein, therapeutic drugs, tumor markers, and certain viral antigen. Okay, so again, nephelometry, do not forget that. Turbidimetry is the measurement of the black light. Nephelometry is the measurement of a scattered light. So, for quality control and quality assurance management, these are some of the reminders. So we can avoid cross-reactivity. We do not want cross-reactivity because this will result to false positive reaction by using monoclonal antibodies directed against antigenic determinant unique to a particular antigen. Okay, so monoclonal antibodies, okay, will provide what? Specificity to prevent false positive reaction. Then, we should be able to store the reagents properly and check for expiration dates. Okay, so kailangan meron expiration dates, no? And then we account for sensitivity and specificity of specific test kits being used. And be aware that a negative result does not rule out the presence of the disease or antigen. Katulad nga ng sinabi ko, maybe you are testing it at an early stage. So you have to wait for several days before you can measure again. Okay, so there you have it, the agglutination and precipitation reaction.